Modern engineering teams are under significant pressure to deploy AI features quickly. To manage this speed, we rely on LLM evaluators, automated judges capable of grading output for relevance and tone at a scale exceeding human capability. Because live A/B tests are often viewed as a slow and expensive part of the process, teams are frequently tempted to treat these automated evals as a direct replacement for experimentation. This creates a fork in the deployment pipeline. An idea goes down path A for an automated check, or path B for a live test. Treating them as interchangeable assumes they do the same job, which flaws how we evaluate performance. Since these two tools measure different things, we must change how we organize the deployment pipeline. Moving away from the fork requires a different structure, the evaluation funnel. In this model, every proposed change must pass through the LLM eval layer first. Only the ideas that meet our quality standards are permitted to enter the live A/B experiment layer. This provides a high-scale, low-cost filter. The goal is to catch and discard broken or irrelevant candidates before they ever reach a real user. By filtering out the noise upstream, LLM evals increase the likelihood that the remaining experiments will actually yield a positive result. The logic for this upstream filter becomes clear when we look at the baseline statistics for product iteration. This grid represents 100 launched A/B tests. At Spotify, only about 12% of these tests end in a positive result that can actually be shipped. This means 88% of the engineering bandwidth spent on live testing is consumed by ideas that don't move the product forward. These numbers demonstrate the hidden value of testing. It prevents us from shipping ideas that aren't ready, but it also shows that experiment bandwidth is a finite, expensive resource. The funnel acts as a defense mechanism, ensuring that only the most promising ideas reach the live testing phase. This defines the specific role of the LLM eval layer, verification. It checks if the output conforms to our specific quality standards. Take the scenario of a team building a judge to detect trust-breaking content, like a recommendation that is a poor fit for a specific user. The automated judge identifies structural patterns in these bad recommendations that the engineering team might have missed, allowing them to implement a fix. Once the fix is live, the judge can verify the improvement by confirming a successful drop in the number of flagged violations. Verification proves the implementation is technically sound, but it cannot measure the impact on the person using the app. An automated judge can't tell you if reducing bad recommendations actually saved user trust. It cannot see if a technical fix stopped the slow, quiet process of a user losing interest in the service. To answer that, we need the A/B experiment layer for validation, testing how real users and complex systems respond to the change. This requires looking at guardrail metrics, the secondary parts of the system we aren't trying to change but need to protect. In complex systems, fixing one problem can often break another. You might see your primary metric improve while a secondary metric crashes. In fact, Spotify rolls back about 42% of launched experiments because they cause a regression in the secondary metrics. These are issues no offline eval can find, things like a drop in session length, higher crash rates, or long-term erosion in user retention. An LLM eval verifies quality in a single dimension, but the experiment validates the total impact on a life system. To trust this funnel, we have to acknowledge that LLM eval scores are proxies. They are temporary stand-ins for the real-world outcomes we care about. This leads to the risk of proxy drift, where a judge starts to reward surface-level patterns that don't actually reflect a better user experience. We visualize this relationship on a matrix. The y-axis tracks the LLM judge score, and the x-axis tracks A/B test engagement. When both scores are high, it's validated. The judge matches the user. But if the judge highly scores a variant that users reject, the system is miscalibrated. We saw this when Anthropic released Opus 4.5. Traditional coding evals showed no progress, yet the model was actually performing significantly better on the long-term tasks that live experiments would have captured. Without a check against live behavior, an LLM score is a sophisticated opinion. It lacks the grounding provided by empirical evidence. To fix this calibration gap, you must run your LLM evals on the actual data generated during the A/B test itself. If we return to our funnel diagram, we have the eval layer filtering ideas before the experiment layer. Now we add a feedback loop. We take the results from the live experiment and use them to calibrate the judge at the top. By measuring the distance between what the judge liked and what the users liked, we find the diagnostic data needed to improve our eval prompts. This cycle allows the automated judge to become more accurate as it aligns more closely with real-world outcomes over time. A rigorous engineering culture uses the funnel to find the best ideas before the experiment and uses the live data to refine the judges afterward. Success comes from making the system simple enough to use and rigorous enough to trust.